Why does heat defy our intuition when we look at nanomaterials? Let's explore one of the most fascinating puzzles in modern physics. Imagine heat flowing through materials at the nanoscale. What we observe challenges everything we thought we knew about thermal conductivity. Let's start with what we know. Diamond has been the gold standard for thermal conductivity for decades. For most of history, diamond was considered nature's best heat conductor, with remarkable thermal properties. Diamond has a thermal conductivity of approximately 2,200 watts per meter Kelvin, which is extraordinarily high. Diamond's crystal structure is a perfect three-dimensional lattice of carbon atoms, allowing phonons to travel with minimal scattering. But why is diamond so exceptional at conducting heat? The answer lies in its structure and atomic bonds. Diamond has incredibly strong covalent bonds combined with a perfect crystal structure, allowing vibrations to propagate efficiently. Now let's talk about carbon nanotubes, the material that broke all the records. A carbon nanotube is essentially a rolled-up sheet of graphene, creating a hollow cylinder just nanometers wide. Individual carbon nanotubes have been measured with thermal conductivities around 3,500 watts per meter Kelvin. This is about 60% better than diamond, making it the champion heat conductor in the universe. This raises a fascinating question. How can a hollow tube made of the same carbon atoms beat solid diamond at conducting heat? The answer is ballistic phonon transport. In a perfect nanotube, phonons travel without scattering over long distances. Think of it like a perfect highway for heat. Phonons zip through without hitting any obstacles, maximizing heat transfer. To understand this paradox, we need to look at Fourier's law of heat conduction. Fourier's law states that heat flux Q equals negative thermal conductivity, K, times the temperature gradient. At the microscopic level, thermal conductivity equals 1/3 times specific heat C times phonon velocity V times mean free path lambda. C is the heat capacity per unit volume, V is how fast phonons travel, and lambda is how far they go before scattering. In carbon nanotubes, the mean free path can be several micrometers long, which is enormous at the nanoscale. In diamond, the mean free path is only about 300 nanometers due to phonon-phonon scattering. Now here's where things get really strange. When we make thin films from these materials, something unexpected happens. A thin film is just what it sounds like, a layer of material that's incredibly thin, often just tens of nanometers thick. We'd expect thin films, made from high conductivity materials, to maintain their excellent thermal properties. But in reality, the thermal conductivity drops dramatically, sometimes by factors of 10 or more. The film's conductivity K film is much less than the bulk conductivity K bulk. So what's going wrong? Why does making a thin film destroy the thermal conductivity? The answer lies in what happens when the material dimensions become comparable to the phonon mean free path. When the film thickness is less than the mean free path, phonons constantly hit the boundaries and scatter. The effective mean free path is given by 1 over the sum of 1 over bulk mean free path plus 1 over film thickness d. When the film thickness d becomes small compared to the bulk mean free path, the effective mean free path collapses. This graph shows how thermal conductivity drops as film thickness decreases. Notice the sharp decline below 20 nanometers. Let's work through a concrete numerical example to see the magnitude of this effect. Consider a thin film made from aligned carbon nanotubes, which should theoretically be excellent heat conductors. Individual CNT mean free path is about 1,000 nanometers or 1 micrometer, but our film thickness is only 20 nanometers. Using our formula, the effective mean free path becomes approximately 19.6 nanometers, nearly equal to the film thickness. This means the film conductivity is only about 2% of the bulk value. The conductivity has dropped by a factor of 50. We get a devastating 98% reduction in thermal conductivity, even though we're using the same material. But there's another critical factor we haven't discussed yet: interface resistance. At any interface between materials or grains, there's a thermal resistance called the Kapitsa resistance. Kapitsa resistance Rk equals the temperature jump delta T divided by the heat flux Q across the interface. Typical Kapitsa resistance values are around 10 to the minus 8 Kelvin meter squared per watt. Total thermal resistance equals length L over bulk conductivity K plus the number of interfaces N times the Kapitsa resistance. In polycrystalline thin films, you have many grain boundaries, so N becomes very large per unit length. Let's dive deeper into why phonons behave so differently at small scales. Think of phonons as particles carrying heat. When they hit a boundary, they scatter in random directions, losing their organized flow. There are three main types of scattering processes that limit phonon transport. First, umclap scattering occurs when two phonons collide and create a third phonon with momentum outside the Brillouin zone. Second, boundary scattering happens when phonons hit surfaces or interfaces. Third, defect scattering occurs when phonons encounter impurities or structural defects. The total scattering rate is the sum of all these individual scattering rates. This is Matheson's rule. 1 over total mean free path equals the sum of 1 over each individual mean free path contribution. The thermal conductivity reversal also depends strongly on temperature in surprising ways. At low temperatures, bulk materials show peak conductivity, but thin films have already saturated due to boundary scattering. At high temperatures, conductivity decreases as 1 over T due to increased umclap scattering. At low temperatures, conductivity increases as T cubed due to the increasing heat capacity. Thin films lose the low temperature enhancement because boundary scattering dominates regardless of temperature. This thermal conductivity reversal has huge implications for real-world technology. In microelectronics, we're facing a heat management crisis as chips get smaller and denser. Modern computer chips have interconnects that are just tens of nanometers wide, right in the regime where thermal conductivity collapses. Power densities in modern processors exceed 100 watts per square centimeter and are still rising. For thermoelectric devices that convert heat to electricity, we actually want low thermal conductivity, so nanostructuring helps. Thermal barrier coatings for jet engines deliberately use nanostructured materials to exploit this conductivity reduction. So how do we overcome this limitation? Researchers are finding clever ways around the boundary problem. One strategy is to create perfectly aligned nanotube arrays where heat flows along the tube axis, avoiding grain boundaries. In aligned arrays, heat flows parallel to the tubes, taking advantage of the ballistic transport within each tube. Second strategy is interface engineering, where we modify interfaces to reduce Kapitsa resistance. Third, we can try to preserve phonon coherence by creating superlattices with carefully designed layer thicknesses. Superlattices can actually have higher conductivity than random nanostructures because of coherent phonon tunneling. At the smallest scales, quantum effects become important, and classical heat transport breaks down completely. When material dimensions approach the atomic scale, we enter a regime where quantum mechanics governs heat flow. The quantum of thermal conductance is pi squared k, b squared t over 3h, times the number of conduction channels, g. Heat flows through quantized channels, and you can't have fractional channels. This sets a fundamental limit. Single molecule junctions represent the ultimate limit where thermal conductance is completely quantized. Let's summarize why heat transport defies our everyday intuition at the nanoscale. In bulk materials, phonons have long mean free paths and high conductivity. In thin films, boundary scattering becomes dominant, destroying the mean free path advantage. The critical parameter is the ratio of film thickness to bulk mean free path. When this ratio is small, conductivity collapses. When thickness d is less than mean free path lambda, effective conductivity scales linearly with this ratio. Multiple interfaces in polycrystalline or composite films add substantial thermal resistance. At the smallest scales, quantum mechanics takes over and thermal conductance becomes quantized. We're witnessing a transition from classical to quantum thermal transport as we push materials to their limits. What does this mean for the future of technology and thermal management? The semiconductor industry wants to keep shrinking transistors, but thermal management is becoming the limiting factor. This challenge drives innovation in novel materials like graphene, boron nitride, and engineered nanostructures. The key insight is that we must engineer phonon transport just as carefully as we engineer electron transport. Future devices will need sophisticated thermal management architectures with carefully designed heat-spreading layers. The thermal conductivity reversal teaches us profound lessons about the physics of small things. What works beautifully in bulk materials can fail completely at the nanoscale due to size effects. At small scales, boundaries and interfaces matter far more than the intrinsic bulk properties. Our intuition from the macroscopic world completely breaks down when length scales become comparable to fundamental length scales. Nanotechnology is not simply scaled-down conventional technology, it's fundamentally different physics. This is why nanotechnology is so exciting and challenging. We're exploring regimes where entirely new physics emerges. Thank you for joining me on this journey through the counterintuitive world of nanoscale heat transport.